All right, greetings, tech artists. All right, we are going to talk about texture mapping and HLSL. And because it is very easy to do once you understand the core concept, and it is kind of like one of the first things we need to do in order to provide, create some interesting looks in our world while we're creating HLSL. Boom, boom, boom. All right. Now, as far as texture mapping is concerned, remember that the UV texture coordinates are provided at each vertex. That means each vertex can be chosen. You don't have to do this now, but each vertex can have U coordinates and V coordinates, at least one set. It can have multiple sets, but ideally, you want it to have at least one set of UV coordinates. Now, the coordinates are looked up during the lookup corresponding on a 2D map. So that means there is a 2D map that corresponds to the coordinates that are on each vertex. And then the colors are interpolated from the triangles to the vertices using bilinear interpolation. Bilinear interpolation is a way of getting vertex information from one vertex to another spread over multiple pixels. All right. Now, as far as DirectX is concerned, if we're looking at a texture map, if you look on the upper left-hand corner, that is where the U00 is found on that image. So 00 corresponds to the upper left-hand corner, and then the values of U travel from 0 to 1 across the top, and the V values travel from 0 to 1 up, from the left edge, from the upper left edge down to the lower left edge. And as far as texture mapping concept is concerned, if we have an image, as what's wrapped right here, and then it's mapped to UV coordinates sitting on side of a polygon, then it is mapped and projected onto the box as seen in this photo here. Or it could be wrapped around an object, like, for example, this 3D object has 3D texture coordinates wrapped around it such that you get this two-dimensional map, and it's wrapped around the object to make it appear like a globe. All right, now we're going to show how to do this in Shader Tool. So if you would please crack open Shader Tool, and we will get ready to rock and roll, okay? I'm going to go ahead first. I'm going to go and create a brand new DirectX project. I'm going to click on New, and then I'm going to make sure that it is located in the correct location. And here it is, my Shader Tool folder, yes. And then I'm going to call this, click on here, I'm going to call it Texture Mapping. That is the name of my project. And then I'm going to click OK. Now we have the blank open object. We're going to right click on here. We're going to throw an effect, click on the beaker, and then we have a blank effect. I'm going to hit the little crayon there, the little marker here, and then I'm going to call this texture mapping for my actual HLSL script. So I'm going to call it texture mapping. Click OK. And there we go. There's my texture mapping.fx file. And I'm going to see if I can increase the size on this. Well, let's put some stuff on here. Okay, one of the things that I didn't do earlier is that to show you folks how to create comments. So I'm going to put comments on here. Comments can be done one of two ways. The first way is to make it a single line, and that's done with a / let's say this is an example of single line comments. Look at that, I spelled it wrong. But notice that it is purple when done in Shader Tool. And if you wanted to, you could do multi-line, and the multi-line is achieved with a backslash and a star, and say, this is an example. And then you could put here of a multi-line multi-line, and then I'm just going to finish this right here with a star and another forward slash or a multi-line comment statement. And it's finished off with a star and another forward slash. Now, good thing it doesn't grade my spelling because my spelling is atrocious, but this is how it's created a multi-line example. So if we click on here, go back to there. Now, if we save this and then go compile, we've got no problems about it. Okay, gang, in order to start making our HLSL look good, what we're going to do, I'm going to put in is using the comments in order to create barriers in between sections of my script. So I'm going to create a section called my resources. So I'm going to click a forward slash star right across and click resources. And these are just kind of general utilities of what we can do to set this up. All right, remember how I said that HLSL was a very primitive C type language? Well, that includes a C preprocessor. And in order to do so, I'll give you an example of it. And a C preprocessor comment starts with a hashtag, and I'm going to put define, and then here's the name of my variable, flip underscore texture. And here's its value, 1. Very primitive, I know. But what this does, flip texture Y. I'm going to change that to flip texture Y so I'm going to stay consistent with my notes. Okay, so what this does is that this is a preprocessor so that it goes and looks through the entire script, and wherever it finds flip texture Y, it replaces with the value of 1. Very simple, it just replaces everything. And now we're going to define some global values to be defined by user. And what we did last time was we had the worldview projection matrix produced by the camera. Now we're going to change that up a little bit so that we have a little bit of control. And so instead of calling it a float 4x4, we're just going to call this a matrix. And we're going to call matrix world, matrix view, and yes, this should be not a matrix. And the last one is matrix world view. I'm going to call this projection. Okay, so that means we're going to have a world matrix, a view matrix, and a projection matrix coming at us. And now what we're going to do is we're going to create a helper function. Now the helper function is going to be another pre-processed element that is going to flip our texture coordinates when we want to. Remember, and let's show my notes here. If we look back here, notice that the upper left-hand corner is where the origin is, and the lower right-hand corner is where the 1, 1 is. Now, this could be upside down, and in GLSL, it's actually flipped. In HLSL, it's definitely like that. And so we don't know if we're going to be dealing with HLSL or GLSL. And so what we're going to do is we're going to put in a little statement here that's going to guarantee it flip. Because we're dealing with HLSL, we want to flip our textures. So I'm going to come right over here, and we're going to write a little script, a utility function, if you would, that's going to help us do that. So I'm going to put a little bit here. I'm going to call this utility functions. All right, I'm going to return a float too. That's because UVs, one for U, one for V, that's a float too. I'm going to call this get underscore corrected underscore texture underscore coordinates. Get underscore texture texture coordinates. I gotta spell this correctly because this is gonna come back to haunt me. Texture coordinates. And as input, we're going to put float2. We're going to put in our regular coordinates. Float2, I'm just going to put texture coordinate. So all that we're going to do is get a texture coordinate as input. And then we're going to open it up with curly brackets. We're going to close with some curly brackets. Now, the reason why we're doing this pre-processing, it's mostly for heritage. We don't have to worry about this too much. But in the old days, we had to worry about our scripts and our shaders being too large. And so what we're doing is going to replace with the pre-processing is going to make things more concise. And you'll see what I'm getting at. And I imagine that even though the memory is not as big of a concern as it used to be, I will see that it still helps. You'll still identify this and people still like keeping it. And so we're going to do it with pound, and we're going to say if flip underscore texture underscore y. So we're going to say if flip underscore texture y, and that has to be a hash if flip underscore texture y, then return float2. We're going to go texture coordinate dot x, and then 1.0 minus texture coordinate dot y. And so what this is doing is it's going to flip it's going to flip the value of y upside down. So basically that's what it's going to do. And we're going to finish this if statement with a pound else, and then return texture coordinate. So Matt, in other words, don't do anything. Just leave it right as is. And then we have to finish this off with a pound and if. Okay, so what this is basically doing is that during the compilation stage of the shader, it looks to see if flip texture y value has been set, and which it has. So if it has been, then it uses this statement, return float2, with this over where the y value is going to be, or the y coordinate is going to be clipped. Now, during the pre-processing, if flip texture y was 0 or it was false, then it's going to just put this statement in here. And so ultimately, when it gets compiled down, our utility function gets shrunk in size. So it comes from this down to this. All right, like I said, this is like during old-fashioned. We don't have to worry so much about it these days, but ultimately, shaders come and shaders go speed, and so ultimately, we don't have to do an if statement in this. We could just go ahead and just use either the inversion, or we could just use the texture coordinates as is. So ultimately, this helps speed things up. Okay, now we're going to put in some render states. Got that in there. We're going to put render states. Okay, I'm going to fix this to make it look good. Okay, we've got a render states. Now, for the render states, we want the rasterizer state. So we're just going to declare this as a struct. So we're going to go rasterizer state, and we're going to use the same one that we used last week, and that is disable culling. And we're going to start this with an open curly brackets, then close curly brackets, and because this is a struct, we have to terminate that with a semicolon. And then we say cull mode equals none. Okay, so there is our rasterizer state. So we've got that set. All right, gang. Now, what we have to worry about is we're going to be using the HLSL texture usage. And when we do that, we have to just worry about 3 steps. And the 3 steps that we worry about are these. Come on, let's go. Let's see this. No, you're not going to show? Okay, there it is. No, we don't want to see a monkey sitting on the throne. All right. There's a 3-step process. First, you have to declare a texture object. We we have to create an object called a texture object in order to be used. Then once we declared it, then we have to declare and initialize a texture sampler. So we have to create another variable called a texture sampler, and that has got to get created too. And then the sample texture is going to be used inside of our pixel shader using the declared sampler. So we've got to have these 3 things. And these 3 things even continue to this day. If you look into Unreal, you realize that there are 2 texture objects. There's the texture object and the texture sampler object. And both must be present in Unreal. And if you don't believe me, go ahead and check it out. So let's go ahead and put that inside of the code here. And then we're going to create a separate section here just for texture mapping. Texture mapping. Okay, first we're going to create our texture object, and that's going to be created by our user. Now this is the external object that would be used to import and declare, this is going to be our texture image. So texture object to be declared or defined. Yeah, let's make it defined by user. All right, and here it is, texture 2D, and then we want to call this color texture. Okay, so this color texture is going to get defined by the user for us. And now what we have to do is we've got our texture object, so we have to create our texture sampler. I'm going to put a little bit of space here. I'm going to call texture sampler object. And you got it. But this is also a struct, so we're going to call it a sampler state, and then we're going to call it color sampler. And because it's a struct, it has an open curly brackets, a closed curly brackets, and a semicolon terminating this. But what's the insides of this? Now, I'm just going to give it to you what the insides of this, and we'll explain what this actually means in just a little bit, so please hold on to your britches. And the first attribute that we're going to be defining here is a filter. So filter equals, and in this situation, copy this exactly, all caps, min underscore mag underscore mip underscore linear. This is not the name or the lyrics to a pop song. This is actually has a real definitive structure, and we'll go into this a little bit later. Okay, now we have to define how we want to duplicate or repeat our U addresses. So address U is our next attribute. Next, address U equals wrap. We'll explain what that is in a little bit. And address B equals, make this a wrap as well. Okay, there's our, I have to change the name of that. This is lowercase. Yep. So there it is, gang. Rasterizer state, there's sampler state. Okay, it is recognized. All right, now what we're going to do is create our data structures. Now our data structures is mostly wrapped around what is going in and out of our vertex structures. So I'm going to declare this section as data structure. Call this data structures. And we're going to create our first struct, and let's call it vs underscore input. So this is the data that is coming into our vertex shader from the attribute assembler, and this is what's going to be coming in for every vertex. We're going to open curly bracket, close curly brackets because this is a struct. We're going to put a semicolon in there, and we're going to start out with float for object position, and we're going to create this to be a semantic is position, and then float to, which is texture coordinate, and we're going to call this with a semantic text coord. All right, so we've got that set. So let's go ahead. That's the VS input. So let's go ahead and create the VS output. And for that, I'm going to create almost a duplicate of that. And I'm going to call this struct VS output. And then the float for is just going to be called, I'm going to call this just position. And then this does have to have the special semantic SV underscore position. Notice that it's in purple. And the texture, let's see, this should be lowercase. Let me put this back in lowercase. Texture coordinate. Now, it doesn't have to be lowercase, but I'm keeping it in lowercase so that it will correspond to my notes and then I won't screw things up. And so I'm just duplicating that attribute right over again. So we have our VS input and our VS output. Okay, we're going to start right off with the pixel shader, which is kind of in the opposite direction, but we'll get around to creating the vertex shader. And the reason why I want to do the pixel shader first is because I want to show you how to do it. We've defined our texture object. We defined our texture sampler object. And so how do we actually access it? So we're going to go and create this next section to be our pixel shader. And we're going to call this float for texture pixel shader. And for the input, we're going to say it as VS underscore output. And our in name is going to be in. And we're going to create a semantic. Now, this semantic does have to take place, and we do have to do this. We're going to call this SV underscore target, or as if my French friend would say, target. And because this is a function, we're going to start off with a curly bracket and finish with a curly bracket. And then we're going to just type in return, and we have our color texture object right up here. So we're going to say color texture, which is the name of our object. And here we're going to call its method. And the method that we're going to call is called sample. And what we're going to do is we're going to call our color sampler, which references to this, which is the min, mag, mip, and linear, wrap, and wrap. And then we want our texture coordinates that it corresponds to. So it's in dot texture coordinate. Nope, they finish that with a parenthesis and then a semicolon. All right, I'm going to go ahead and save this. And undeclared identified texture coordinate. Okay, I misspelled it. So that's in line 17 all the way up here. So texture coordinate, there it is. Okay, I misspelled it. I'm going to hit Control S. Yep, there it is. That fixed it. Okay, now we know everything's good. We've got rid of our typo errors, and so we are good to go. Now we're going to create the vertex shader. And I like to put my vertex shaders in front of my pixel shaders. You don't have to do this. It's just something that I like to do. I'll call this section vertex shaders. Okay. And so this is coming, the output of my vertex shader is my vertex shader output data. So we're going to declare the type of my function as vs underscore output. And we're going to call this texture vertex shader. Okay, so that's the name of my vertex shader. And then, so therefore, our input is going to be a vs input struct, vs underscore input in. All right, and we're going to start this off with curly brackets. Going to finish it off with curly brackets. Let's enter out the information in between. Since we know we're going to be returning a vs output, let's declare a vs output object, vs output, and we're going to call it out, and to say equals. And what we're going to have to do is we're going to have to declare a vs output object, and then we're going to have to cast it to 0, and otherwise initialize all its values to have no value. And then we're going to type in here out dot position. Okay, remember the purpose of, no, that's not all cap, this is lowercase. Remember, the purpose of the vertex position is to take each vertex and then transfer it into worldview projection. And we're going to do that to all three of this, because remember, we're now importing into 3 different textures. We get worldview projection. So we're going to have to take our vertex position and we're going to multiply it by the world, then the view, and then the projection matrix. And so we're going to do that, say, okay, multiply in dot position. Oh, it's called object position, my bad. Object position, and we're going to multiply that by the world matrix. And then what we're going to do is we're going to multiply the result of that against the view matrix. And so we're going to do a multiply around that, and then put here this comma, and then we're going to use the view matrix. And then we're going to multiply it one more. We're going to say mul. And then we're going to multiply this by the projection matrix. So we've got, I can put a semicolon there. So we've got one line to do everything about multiplying our object position against the worldview projection matrices. We're doing all 3 all at once. And then I'm going to put a little note here. Flip the texture coordinate axes. Now we're going to flip the texture coordinate axes because this is an HLSL, and say because HLSL, because they say it has to be that way. So we're going to say out dot texture coordinate equals, and now we're going to call our little function that we created up here, which is this bad boy, get corrected texture coordinates. And I'm just going to put that right in here. And then I'm going to put in the texture coordinate. All right, so we got that. And now all we have to do now is just return out. All right, oops, that's return B. We don't want that. That's going to create a error. So let's go ahead and save this and make sure that it compiles. And it does indeed compile. All right, gang, now all we have to do is create our technique. And I'm not going to type this in slow. We've created techniques before, so I'm just going to copy a technique that I already have created. and we're going to see this a zillion times, and so we already saw it ad nauseum last week, and so we're just going to just go through it this way and take a look at it this way, and since this is a recording, then we're just going to make it look the same as all the others. And I'm going to put this across here. All right. So we have our set vertex shader is our compile shader. We've got vertex shader model 5, and we've got our texture vertex shader, which is right here. Here's our set our geometry shader to null. Set pixel shader. We're going to do the compile shader, and we've got pixel shader 5.0, and here's our texture pixel shader. And then here's our set rasterizer say disable culling, which is set up here. There we go. And so everything should be good. Now, if I go ahead and save this and compile it, okay, line 78. That means we are missing a unexpected token. And so we are missing here is a semicolon someplace. And is it here? Texture sample in the texture coordinate. Okay. And hold on a second. I'm going to try to figure out where this is. And I think I know where this is problematic. Notice that I'm missing a parentheses here. So if I click on here, come on, give me the parentheses. There, so we have 3 parentheses. Let's go ahead and compile, and it goes away. So that was my problem. So let's go ahead, build, and display this. So we've got our texture, we got our shader. Now let's go ahead and go into scene, and then grab a draw call, and we're going to hook the draw state up into here. And so we have all of our information here. We have an output node, and I'm going to drop down a content and grab a primitives. And for this, I'm going to want to get in a sphere. And then I'm going to drop that right into here. And then now what we need is the world view projection matrices. And so for the world matrix, so I'm going to do is I'm going to go ahead and grab types, and then I'm going to grab this rotation matrix on here. I know it's not a full world transformation matrix, but for this situation, this is really all I need right now. So I'm going to drop that right into there. And all I'm going to do is grab the camera now. And now I'm going to grab the scene. There's my camera. And then I'm going to put the view matrix into view matrix and projection into the projection matrix. And the only thing I need now is my color texture. And so I'm going to right click on here, and then I'm going to look for content, and there's my texture node. So I'm going to click on texture node, and there it is. And I've already got I should already have a texture map. Any texture map will work. So I'm going to look for a texture map that is on here, and I'm going to go in here, look for shader tool, light types. No, I don't want it in there. And so let's see, texture mapping, TM. So baby's first shader, yeah, we'll just grab it right from there. Effects, oh, it's not in here. So let's see, baby's first shader, yeah, let's grab it from baby. Let's see, okay, texture file, PNG, effects. Oh, okay, I got it. So maybe it would be in there. So I'm going to look into this right here. The textures. Okay, well, there's the good old Oingo Boingo default. And so we got that. And so I'm going to put that right into color textures. And we should be good to go. All we need is a frame buffer. So I'm going to look under here and look under scene. And there is a render target. All I have to do is hook that up into here, and voila, we have our render target. So notice that we've got a texture thing. If we go in here and then we move our camera around, we can see the skull wrapped around there, and we pull that around here. And so what we're doing is rotating the camera in order to get the look that we want. Notice that by default, we have the world is set here, and it's to a default world position, and the view and the projection matrix are coming from the camera. So I'm going to reset my view here, and so that's going to put this on here. Now, what I'm going to do is I'm going to rotate the object from the world matrix, and so now I'm using the world matrix to thing. Now, when I click on this button to reset it, nothing resets. Why? It's because my rotation matrix is showing where it is, but I can still look around here, and that will reset, but not to where it is. Okay, so that is our texture mapping technique. Nice and simple, and we can get lots of detail if we wanted to see what this looks like. If we were to put this on a box, we could put it on a box, and whoop, there it is. And my box is all do-wacky. It's because my rotation matrix is all screwed up. And so I found that the best thing to do here is just kill that rotation matrix and go into types, go grab a new rotation matrix, and we could put that in. That is our new world matrix. Okay, now let's go back to our sampler state. Now, what is this gobbledygook filter, min-mag, mip, linear, and address U and address V, wrap, wrapper? Okay, what does all of that mean? Okay, let's go back to our display notes. Oh gosh, okay. Let's go ahead and move this forward. Okay, sometimes there are more pixels than there are texels. Now, reminder, a texel is what each dot on a texture map corresponds to. And so when there are more pixels on the screen than there are texels, then what we've got to do is we've got to blow the thing up, and that's called magnification. Now, sometimes when there are more pixels, they cover up more than one texel. So this is a little bit more complicated. And so in order to do it, we don't do the opposite of magnification. What we do is do something called MIP mapping. And MIP mapping is a little bit of a different process. Let me see if I can describe this a little bit better. When we go into magnification, what we have here is the texture coordinate, and here's the portion of the texel. And then we just basically fill the texel in to fill the pixel. But what if there are more than one texel? Here, this texel, this texel, this texel, this, and then we have to render in this particular pixel. How do we minify that? Well, this is where we use a process called min mapping. Now, you've heard of min mapping before, and I know that you've heard of LODs and levels of detail, and you never probably knew what it means before, but here is your definition, so you've got no excuse not to know what this means now. All right, now when you magnify stuff, you can use three different techniques. You can use point filtering, linear interpolation, and isotropic filtering. Point filtering is that you use the texel color closest to the pixel center, and this gives you the lowest quality in a blocky thing. Now you'll say, hey, wait a second, that looks like Duke Nukem, or this looks like Doom. Well, there's a reason for that. It's because it was a very simple program. Doom was a very simple program, and it stored the texture values in a very tiny space, so therefore the texel density was smaller than the actual pixels that it was putting onto. And so therefore it just kind of found the nearest pixel, and it just magnified that, found the nearest texel, and then just magnified it to fit the nearest thing. Now this does produce this is the fastest technique, but it also is the lowest quality, and it makes stuff look blocky, like from Duke Nukem or Doom. All right, linear interpolation is a little bit more thing. It's called bilinear interpolation. You remember I used bilinear interpolation before? Well, let's just say that we've got 4 texels here, but the pixel that we want is going to fit somewhere in between. So what value do we use? Well, we figured out where the value of this pixel lies in between these texels. And then we figure out where does it fit horizontally, and so that gives us the U value. And then the V value is done wherever the point fits, somewhere in between there. So the U values are interpolated and the V value is interpolated, and this produces something that looks a lot simpler and it looks a lot better. It's slower, but it's smoother. And then we have the third one is anisotropic filtering, and it's good for objects which are oblique to the camera. You mean not necessarily facing the camera, but almost perpendicular to the camera. And this results in distortion, reduced distortion, and improves the overall rendering output quality. And this is the most expensive, but it is the best looking. So if we notice here, if we had a texture map put on our world, excuse me, and it's projected onto this, you'll notice that if we use the texture mapping, the bilinear interpolation, it gets blurry right up top here. If we use anisotropic comparison, then we end up with something that looks pretty good all the way through. Now, texture minification, as I was mentioning before, is a little bit more complicated, and ignoring just the texels and just hoping that it just looks good, kind of like the magnification, it doesn't look so good. It just looks for it. Now, ultimately, what we would rather have is a downsampled texture image that would be mapped pretty close to the texel size, the pixel size. And that's what's called MIP mapping. And you didn't know this, but whenever an object gets turned into a texture object or being into that, so what it does is it converts your texture image into a whole bunch of other texture images. It's pre-baked, and this is what it does every time. And so basically, it takes the texture image, and then it creates a duplicate that is half in the U and half in the V, and then it puts that on the texture object, and it takes that half-wise again, and then half-wise again, half-wise again, all the way down to it only goes down into one texel size. So if we look at our texel object or our texture object, once all this like, our texture object looks like this. We started by, here's the full-size texture image, and here is the next object that's half as big, then half as big, half as big. Now notice that you've said, well, this must create a huge overhead. Our textures are getting larger. Yeah, they are getting larger, but not actually a very significant amount. And you'll notice that even though we are using all this, the texture amount on here, it doesn't fill up. So here's some extra wasted space. Now, believe it or not, this is done for every image that's brought into any texture image. It's just that you, up until this point in time, have never seen this before, but now you are aware. You'll never see texture objects again for the rest of your life. Okay, now, when it has to evaluate the minification. Now, there's three ways of evaluating. You can either use point filtering, which gives you the nearest MIP level, or you can use linear filtering that selects the two surrounding MIP maps, and it does a bilinear interpolation, or it could use the anisotropic filtering in order to understand which one is going to be the best MIP value. All right, and so this is where the crazy filter comes from. You really have to define what the minification, the magnification, and the MIPPing is going to be done as. And you declare that in the colors or the sampler state. Now, if you look at this one, it says, well, basically there's only, let's see, 1, 2, 3, there's only 9 different variations that you could possibly have. And the most common 3 ones are going to look just like that. The most common 6 are going to look just like this one. You can have the minimification, the magnification, and the MIPPing is all using point interpolation. And you get all 3 to being done with linear interpolation. And then if you want all 3 to be done with anisotropic, you just say anisotropic. All right, now you could break it up if you wanted to, or if you had to. You could say, okay, make the minimification and the magnification point and make the MIPPing linear. Okay, fine. Or you could make the minification linear, the magnification point, and the MIPPing linear again. I don't know why you would, but like I said. Or you could just go with something like the minimification, the magnification, and the linear interpolation are done with linear, and then mipping is all done with point. Whatever. Okay. I don't know why you would want to mess with it, but once again, like I said, this is an ancient language, and so this is what we'd have to deal with. And so we have the minification, the magnification, and the mipping, and in this case, it's all done linearly. All right, we don't have to do the anisotropic, and so we could just leave it right here at linear. But what about this address U and address V? We're still kind of be doing with wrapping. Okay, now what do you do if the texture coordinates are outside 0 to 1? They could go negative, yeah, no problem. And they could get larger than 1. It could go 0, 1, 1.5, 1.2. Well, this tells the renderer what to do, and there are 4 different methods that you can deal with this. You can either do a wrap, you could do a mirror, you could do a clamping, or you could do a border. Okay, let's take a look at each one of these. Wrapping basically duplicates the entire texture in order to fit the thing. So it just keeps on wrapping right around. So it just keeps on duplicating it. So in this situation, notice that the UV texture coordinates are repeated 3 different times. So how did I do this 3 different times? What I did was I increased the textures space of my object by 3. Now, how did I do that? I did it in the shader. Okay, not real crazy. Let's take a look at what that would be on here. All right, so we've got that on here. So I'm going to look inside my here. And so here in my vertex shader, so we've got the out texture coordinates. So here's the in texture coordinates. All right, so let's just let's create an in. So we say like something in dot texture coordinate dot x, and we're going to say times equals 3. Is this right, or is this Python? Yep, there it is. We duplicated it 3 times. We did 3 all the way across. So let's do this in Z. So I'm going to duplicate this again. And I'm going to set this in texture coordinate, and we're called Y. And there it is, 3 by 3. All right, why? Is it because this was done with wrapping, and we made it larger? But what happens if we go smaller than 1? So, okay, let's do it. So we'll do across. We'll do like 0.5. Okay, so we get half our image, and it only goes to half across. But what if we go and do, what did it go do negative? So let's do negative. So let's call this -1. Yeah. Okay, hit save, and then it flipped all these things around. All right, or if we wanted it 2 horizontally and 3 vertically, we could just leave this at 2. And there we go. All right, so here it is. I'm monkeying with the texture coordinates. We're going to do this lots because when we go into visual effects, this is when things really get interesting. All right, so that was wrapping, but let's look at some of the other things we could have. We could have wrapping, or we could do mirroring. Mirroring is where instead of just duplicating the texture coordinate, it mirrors it left to right and vertically up and down. And so this is where it kind of like flips around. Every time it repeats, it flips. So let's try to take a look at our example here. So let's say, let's move this. So horizontally, let's mirror it. Mirror. And then there they are. These got flipped one way, and there's those flipped the other way. All right. Now, what if we wanted to just leave these as wrapped? And we wanted to make it just vertically to mirror. There you go. It's just the middle ones flip. Okay, so you get the point here. You could really go ape nuts and go crazy all day with this. Okay, let's take a look at those other two techniques. Oops, warp. No, we don't want to warp. We want to wrap. Okay, what about clamping? Clamping takes the last pixel value horizontally and then in the U direction and the V direction, and whatever that color is, it just stretches it right across. It just duplicates it right across. So this is where sometimes when your textures are streaked, and that's because you've got clamping on the color sample. So let's take a look at what that looks like. All right, so we put clamp on here. And so it just gets the right side there. And the bottom side was do clamp. Oh, I spelled it. Ooh, I screwed that up big time. Clamp. Okay. Yeah, there it is. There it is in the lower corner. All right. So we've got the clamping going on here. And let's put this back into wrapping. There they are. And the last one we have to deal with is border. Okay, so what we use is the border color. And so notice that instead of taking the last color, the last U color and the last V color, and then just replicating it around, we use the border color. And so we can do the same thing here. Huh? Let's make this border color. Okay, and so notice the border color. Now, because we haven't defined a color for what border color is, it just made it the background color, whatever the background color. Now, notice that Shader Tool does give us the ability to manipulate this. And so if we go and put a color inside clear color, we can set that value. So if we go ahead and with types and we could put in some color here, and let's just go some sexy magenta. Oh, that's red. Yeah, magenta. Go right up here. If we put that up here, there it is. The whole thing gets wrapped right around here. So it just stretches everything around here. But notice that this actually did put it as the background, and it still didn't put anything out for border color. Now let's see, border color. I don't know. You know what? I realized that I don't know how to set the border color is. I'd have to go look into it. So check back with me if you want the border color. Okay, folks, there you should have enough information on how to do the rest of the homework. And there's all the information that you have on here. So if you have any questions, please swing on by and come across my office, or else text me or send me information, and I'll try to answer you the best that I can. Thank you very much for your time and attention, and we'll see you all again for when we start dealing with light types and light materials. Actually, thank you very much. We'll see you on the flip side.